power system involves many components like generators, transformers, transmission lines, circuit breakers, relays, loads, compensators, etc. All these components are connected in three phases. Representing their interconnection in three-phase diagram is very difficult. So we represent all the interconnections in one reference phase. That's such a diagram is called single line diagram. Okay. So here is an example of a single line diagram. Here you can see the generator G is a three-phase generator which is star connected. You can see adjacent to this one, the connection is also mentioned. It is star connected. The neutral point is grounded through some inductor. Neutral point is grounded through some inductor. Okay. Next, this is a generator bus bar. This is a generator bus bar. The rectangular boxes are circuit breakers. Every circuit breaker will have its relay. And then the T1 is the transformer whose primary is delta connected, whose secondary is star connected, and the star point is solidly grounded without any impedance. If the neutral point is grounded to, then it's called solid grounding, solidly grounded to this one. Again you have a transmission line. So this is the transmission line. You can see where at the beginning of a transmission line there is a circuit breaker, at the end you have a circuit breaker. Again you have one more transformer T2. So the primary of T2 is star connected and solidly grounded. The secondary is delta connected. Again there is a bus. To this bus one synchronous motor is connected. This is a synchronous motor. This synchronous motor is also star connected and its star point is grounded through some inductor. Okay. So single line diagram gives complete details of the interconnection, type of connection of transformer, and the nature of grounding of all neutral points will be represented by the single line diagram. Okay. So it gives complete data, but only it will give the interconnections in one phase. The remaining two-phase interconnections are just a replica of this connections. Okay. Next, how we represent the synchronous machines, what data is required for analysis for the synchronous machines. Here synchronous machines means either it can be synchronous generator or it can be synchronous motor. In the image you can see that if this is a synchronous generator, it is an exciter and this is a prime mover. You can see it is a prime mover. As symbol is prime mover. This is the exciter circuit. In our electrical circuit form, we will model the synchronous generator as a AC voltage source which is connected to some reactance. So this is the modeling of our synchronous generator. Okay. So what data is of importance in synchronous generator? So synchronous generator is in original form, this would be the synchronous generator. In circuit form, we'll model it as a AC voltage source in series with some impedance. But however, in fault analysis, we neglect all resistances. So we only model the reactance of the generator. So in circuit form, we model it as a AC voltage source in series with some reactance. Okay, that is the first point. So this is the synchronous generator representation. Now, what is the important data that is required for our analysis, for our fault analysis? That is, first important data which we require is the three-phase MVA rating of the synchronous machine. The second data which we require is the line-to-line RMS voltage. Of the synchronous machine. Okay. So apart from these two data, we require reactance per phase of synchronous machine. So these three data are very important for our analysis. Okay. So for time being, you remember that a synchronous machine has three reactances. See, first point, what is important is all our synchronous machines that we use in power system analysis are cylindrical rotor synchronous machines. Cylindrical rotor synchronous machine which has only direct axis reactance. So there are three different reactances for a synchronous machine. The first one is called XT double dash, which is subtransient reactance. The second reactance is called XT dash. This is transient reactance of synchronous machine. Transient reactance. So XD is called steady state reactance. So all are the direct axis reactances. Direct axis reactances of cylindrical rotor machines. Okay. So for fault analysis, we will be mainly considering the subtransient reactance. So what are the important data that we require? We require the MVA rating of machine, three-phase MVA rating of machine, line-to-line voltage of the machine, and reactance per phase. Actually, we require all three reactances. We require subtransient reactance per phase, transient reactance per phase, and steady-state reactance per phase. But depending upon the data given, we will be using it. Okay. So that is the point. For example, if you take, let me take a generator whose rating is 11 kV line to line voltage, 500 MVA is the three-phase MVA rating of the machine, and the XT double dash value is say 1.2 ohm per phase. So like this, they will specify the data of the synchronous machine. In case of synchronous motor, also the same thing will be mentioned, but here instead of voltage source, we will treat it as a load. We will treat it as a motor. Understand? That is the representation of synchronous machines. The second is the representation of transformer. So again, a transformer is represented as a single reactance. It is represented as a single reactance in power system network. This is phase, this is neutral, this is the, let us call this X equivalent. That is the, it is represented as a simple series reactance in power system network. Okay, that is a representation. Now data wise, if we come to data, a three-phase transformer. So what data we require? Three-phase MVA rating of transformer, and second data we require is line to line. Third thing is equivalent impedance. Mostly it will be reactance. In most cases it will be reactance. Equivalent impedance or reactance referred to either HV side or LV side. Okay. Sir, first two things are clear. A transformer will have one MVA rating. Let us say 100 MVA transformer, 200 MVA transformer, that is well and good. The second thing is also clear. What is line to line? Suppose it is 33 bar 11 kV transformer. The line to line voltage on the primary side is 33 kV. The line to line voltage on the secondary is 11 kV. So the voltage, line to line voltage ratio is 33 bar 11. 33 bar 11. But what is the third point which you are trying to tell? The equivalent impedance referred to either HV side or LV side. So if you recollect your equivalent circuit of transformer, a transformer you can model it as this impedance is called Z2 and this is the turns ratio N1 N2. This is called Z1. This is V1. This is X0, R0. This is I1. This is I1 dash. This is I2. This voltage is V2. So this voltage is E2. This voltage is E1. So this is the exact equivalent circuit of the transformer where V1 is the primary voltage and V2 is the secondary voltage. Okay. Now this portion is called magnetizing circuit of transformer. Magnetizing circuit of transformer which draws a current of I0, which is the no load current of the transformer. Okay. So in power system analysis, we neglect the magnetizing circuit of the transformer. In power system analysis, whenever we model the transformer, we neglect the magnetizing circuit of the transformer. So when you neglect this portion, what you are going to get? You are going to get this one. So there will not be any difference. We are directly calling this one as I1. Okay. Now, if I calculate the equivalent impedance with respect to primary, that means called Z1 equivalent. So I am calculating the equivalent impedance of the transformer referred to primary side. Then you are going to get Z1 equivalent is equals to, if the turns ratio is 1:A, that is EV, where A value is given by N2 divided by N1. Turns ratio A is given by N2 divided by A1. So Z1 equivalent will become primary linkage impedance Z1 plus secondary linkage impedance Z2 divided by A square. This is the Z1 equivalent. Similarly, if you calculate the equivalent impedance referred to secondary side, Z2 equivalent impedance of the transformer referred to secondary, Z2 equivalent will become here A square into Z1 plus Z2. So these are the equivalent impedance of the transformer with respect to either primary or secondary side, or in other words we can write the equivalent impedance of the transformer referred to either HV side or LV side. So in the power system analysis, he will give either Z1 equivalent or Z2 equivalent. So in our analysis, in the data, they will mention either Z1 equivalent or Z2 equivalent. So the three important things are the three-phase MVA rating of the transformer, line-to-line voltage ratio of transformer, and equivalent impedance. Mostly they will give reactance, equivalent impedance or reactance referred to either HV side or LV side. That will be the data that is required for the power system analysis with respect to transformer. So if you take a simple example, 100 MVA transformer, 33 bar 11 kV, 33 bar 11 kV is the line to line RMS voltage ratio, and 10, you can write this as 2 ohm per phase referred to HV side. Like this the data will be mentioned. That means the equivalent impedance of the transformer with respect to 33 kV side is 2 ohm per phase. 2 ohm per phase. Like this the data of the transformer will be mentioned. So next, how we represent the transmission line? Even transmission line is also represented as a series reactance. Is a simple series reactance. Okay. So what is the data that is important in transmission line? it is the line to line RMS voltage of the transmission, line to line RMS voltage of transmission line. So transmission line voltage. The second is series impedance. Two data will be specified in the transmission line. What is the line to line RMS voltage of the transmission line and the series impedance per phase? For example, it is a 132 kV line whose series impedance is 20 ohm per phase. So like this, the data of the transmission line will be mentioned. Okay. Next, how do we represent loads? Loads, in most of the cases, the loads will be RL loads. They will be represented as a series combination of some resistance and reactance. So this is how we mention the RL loads, represents the RL loads. So data wise, what data is important in terms of load? Line to line voltage, line to line RMS voltage across the load and complex power demanded by load, complex power demand of the load. Okay. So in this way, they mention the load data. For example, 6.6 kV and complex power demanded by the load is 20 plus J15 MVA. So which means the voltage across the load is 6.6 kV and the load is demanding 20 megawatt of real power and 15 MVAR of reactive power. 20 megawatt of real power or active power and it is demanding 15 MVAR of reactive power. This is how we mention the load. Some cases they will mention, second example I am trying to tell, some cases they will mention the data as 6.6 kV, 20 MVA, 0.8 power factor lag. So here, once you know power factor and apparent power, you can usually calculate this. S load will become how much? 20 into 0.8 plus J into 20 into 0.6. This will give the complex, which is 16 plus J, 12. So many MVA, where it is demanding 16 megawatt of real power and 12 MVA of reactive. This is the one more representation. Sometimes they may give 6.6 kV, the voltage is must, and 16 megawatt at 0.8 power factor lag. So he is mentioning the real power and the power factor. From this again you can calculate the complex power absorbed by the load. Okay. So whatever may be the data specified, one is the line to line RMS voltage across the load. Next one is we should be able to mention complex power demanded by the load. This is the data that is required from the various elements in the power system network. Okay. Sir, why we cannot directly analyze the power system? What is the problem? So let us take the circuit that we have considered earlier in the single line diagram. If you directly try to model this circuit, so we can write the generator as a series generator. Next you have the transformer you can write it as Z1, and then after transformer you have a transmission line. Again you have one more transformer. Again you have the secondary side of transformer. Then you are having one more motor. So this is the equivalent circuit of the above single line diagram, where Z1 is this is transformer T1, this is Z2 of the first transformer, this is transmission line impedance, this is Z1 of second transformer, this is transformer T2, this is Z2, and this is the reactance of the generator XDG, This is reactance of the motor. Understand? Here, to analyze the circuit, here the voltage level will be something, let us call this transformer is 11 bar 33 kV and this transformer is 33 bar 6.6 kV. Now what is the voltage here? The voltage at this point is 11,000 divided by root 3 because we have drawn the single phase equivalent of the three phase system. Here the voltage is 11,000 by root 3 volt, whereas here the voltage is 33,000 divided by root 3. Similarly, here the voltage is 33 by root 3 and here the voltage will become 6,600 divided by root 3. So here the current will be different, here current will be different, here current will be different. So you have to simultaneously solve three different circuits and correlate the results, which will become very difficult. Why? Because whenever there is a transformer is present, the voltage level of circuit is changing. So when you take any circuit theory problem, you don't have this problem. Why? Because there is no transformer. The entire circuit is at single voltage level. You can apply your nodal analysis, mesh analysis, superposition theorem, KCL, KVL, and you can easily find out the result. But here, because of the presence of transformer, the voltage level of the circuit is changing suddenly from one voltage to other voltage. So rather than solving one network, we have to solve multiple networks which are at different voltage levels, and then you have to correlate the results. So this will make our life very difficult. That's why direct analysis of power system network is not done. Direct analysis of the power system network is not done. Understand? So we go for per unit system. The presence of transformer. So to bring down the entire network to single voltage level, to avoid the difficulty that is created by transformer and to bring down the entire network to a single voltage level, we go for per unit system. So next, the important topic is per unit system. So per unit value of any physical quantity is defined as the actual value of physical quantity in some unit. Actual value of physical quantity in some units divided by base value of the same physical quantity in same units. So per unit value of any physical quantity, it can be mass, it can be length, it can be quantity, it can be anything. So per unit value of any physical quantity is defined as actual value of the physical quantity in some unit divided by base value of the same physical quantity in same unit. Okay. Suppose the length from town A to town B is say 100 km. Okay, that is the actual distance between town A and town B is how much? 100 kilometers. Then base distance which I am choosing, the unit of base distance should be same in kilometers. You should not mention in millimeter or centimeter or meters. The base value should also have the same unit. Let us take it is the 200 kilometers, the base distance. Then the per unit value of the distance between the town A and town B will become 100 kilometers divided by 200 kilometers. So this is 0.5 per unit. Understand? Suppose if I choose the base distance as 50 kilometer, my base distance is 50 kilometer, then the per unit value will become 100 kilometers divided by 50 kilometers. So this is 2 per unit. So depending upon the base value which we choose, the per unit value of the same physical quantity will change. Understand? So per unit value can be greater than 1 or less than 1 depending upon the base value. Okay. One more example. Suppose a basket contains 80 mangoes. And my base value for mango is say 200. 200 is the base. 200 mangoes is the base value. So per unit value of mangoes will become how much? This will become 2 divided by 5, that is 0.4 per unit. 0.4 per unit. So likewise, you can define per unit value for any physical quantity, but the only thing we have to remember that the unit of the actual value and base value should be same. Understand? Next, when it comes to electrical systems, we basically mainly deal with 4 physical quantities, that are voltage, current, impedance, and powers. So we mainly deal with 4 physical quantities, that is voltage, current, impedance, and powers. Okay. Now, out of all these 4 physical quantities, we choose the base value for 2 physical quantities and we derive base values for the remaining 2 physical quantities. Okay. So, the first point is, in electrical system, we mainly deal with 4 physical quantity, that is voltage, current, impedance, and powers. Okay. So out of 4, we choose base values for 2 physical quantities, that is we choose base value for the power and voltage, and we derive base values for remaining 2 physical quantities, that is current and impedance. Understand? Current and impedance. Okay. So that is the first important point. In electrical system, we mainly deal with 4 physical quantities, that is voltage, current, impedance, and power. Out of 4, we choose base values for 2 physical quantities, preferably power and the voltage, and we derive base values for remaining 2 quantities, that is current and impedance. Okay. One more point which I want to tell you is that complex power means it has both real and reactive power. So base value for all these 3, that is base value for S, base value for P, base value for Q is same, that is SB. The base value for the complex power, real power, and reactive power, it is same. Usually it will be given in MVA. It is called apparent power base. The magnitude of complex power is called apparent power. So when you directly give the data in MVA, it is called apparent power. So the base value for S, base value for P, base value for Q will be same. It will be mentioned as S base. That is MVA base. Similarly, the impedance contains resistance and reactance. So again, the base value for Z, that is impedance, resistance, and reactance, it is same. It is usually mentioned in ZB, base MVA, base impedance. The unit will be ohm. Understand? So you don't get confused. You don't have separate base value for resistance and reactance. It is only Z base. Similarly, for real and reactive power also, the base value is only S base. Okay. So this point you should not forget. Next, what we are having, if you take a single phase system, S is given by, the magnitude of S is given by V into I. If you want complex power, then it is become V into I conjugate. If you only want apparent power, the magnitude, then S is given by V into I in single phase system, where V is the phase to neutral voltage and I is the phase current. Okay. So in terms of base values, their relationship become SB will become VB into IB. So if SB is the base value for single phase circuit, then SB is given by VB into IB. Okay. So now IB will become how much? SB divided by VB. IB will become SB divided by VB. Okay. Next you're having ZB, I can write it as VB divided by IB. Why? Because in a single phase circuit, V is the phase to neutral voltage and I is the per phase current. Then Z is given by V divided by I. Z is given by V divided by I. So in single phase circuit, ZB is given by VB into IB. So which I can write it as ZB is equals to VB divided by, how I can write IB? IB I can write it as SB divided by VB, which will give you VB square divided by S. So Z base is given by base voltage square divided by, that is the first relationship which you have to remember. Second is Z per unit is given by Z actual divided by Z base. So which is equals to the actual value of impedance divided by, what is the Z base value from this relationship? Z base equal to VB square by S base, that is V base square divided by S base. So which will give Z actual into S base divided by V base square. Z actual into S base divided by V base square is the per unit impedance of the per unit impedance formula when you know actual impedance value. This is one more relationship. Okay. So this is the second relationship which you have to remember. The third thing is, let Z per unit 1 is the per unit value of Z actual SB1 and VB1 on a base of SB1, VB1. Z per unit 1 is the per unit value of the Z actual. Let Z per unit 2 is per unit value of same impedance, that is Z actual, on a different base values, say SB2, VB2. Now how I can write? Z per unit 1 is equals to Z actual, the actual impedance, into SB1 divided by VB1 square. Okay, that is, let us call 1. Similarly, Z per unit 2, how I can write? The actual impedance into SB2 base MVA divided by base KV, base voltage square. Let us call this 2. Okay. So if you divide 2 divided by 1, what you are going to get? Z per unit 2 divided by Z per unit 1 is equals to Z actual by Z actual. So by SB1 into VB2 by VB1 whole square. This is the third important relation which you have to remember. Z per unit 2 is equals to Z per unit 1 into SB2 by SB1 into VB2 by VB1 whole square. Okay. So here, if you already know the per unit value of an element on particular base values, if you want to calculate the per unit value on a different base values, then you have to use this formula. So you only have to remember these three formulae. The first formula you have to remember is Z base is equals to VB square by S base. That is the first formula. Okay. Second formula is Z per unit, when you know actual value is given by Z actual into S base divided by VB square. Okay. Third formula is Z per unit 2 is equals to Z per unit 1 into SB2 divided by SB1 into VB2 divided by VB1 whole square. So only if you remember these three formulae, that is good enough. Okay. Here we are trying to calculate the new per unit value, where already we know the old per unit value and old base value. So that means for an element Z per unit 1, is calculated on a base of SB1 and VB1. Let us call them as old base values. Old values. Now I want to calculate the per unit value of the same element on new base values. New base values, let us call them SB2 and VB2. Then my Z per unit new is Z per unit. So I am calculating the Z per unit 2, that is new per unit value on a different base values. So some textbooks will write this formula, same formula as Z per unit new is equals to Z per unit old into S base new base MVA by old base MVA into old base KV by new base KV whole square. Understand? So these three formula you have to remember. Okay. The formulas are exact same for three-phase system as well as single-phase system. There is no difference. But what is the difference between single-phase and three-phase per unit system? We'll only discuss that point and we will close this per unit. So three-phase system, the complex power is given by 3 times V into I. If I calculate the only magnitude of the complex power, S is given by 3 into I. If I want true complex power, that is 3VI conjugate. Okay. So the same value I can write it as S is equals to root 3 into VL into IL, where VL is the line to line voltage of system and IL is the line current. IL is the line current. Okay. Now, similarly, S base, three-phase base MVA will become root 3 VB into IB, where VB is the line-to-line base voltage, and SB is the three-phase base MVA of the system. That is the only change. In single phase, SB is the single phase base MVA, VB is the phase to neutral base voltage, whereas in three phase, your SB is three phase base MVA and VB is the line to line base voltage. Again, from here you can write I base is equals to SB divided by root 3 into VB. Okay. Now, Z base is given by, so in any single phase system or three phase system, the base impedance value is given by phase to neutral base voltage, that is this voltage, phase voltage divided by phase current. Okay, so Z base will become VB divided by root 3. First I have to convert the line to line base voltage into phase to neutral base voltage, that is VB divided by root 3 into IB, because in a star connected system, phase current equal to line current, so I am directly writing IB. So which implies VB divided by root 3. If I write the IB formula from the above relationship, it will become SB divided by root 3 into VB. So this will give you directly VB square divided by SB. Same as in the single phase case. So in single phase system also Z base is given by VB square by SB. Even in three phase it is given by VB square by SB. Okay. So from this the remaining formulas they will repeat in the same fashion. So we need not compute. So only difference that you have to remember between single phase and three phase system is, in single phase system your base voltage is phase to neutral base voltage, whereas in three phase system your base voltage is line to line base voltage. In single phase system your base MVA is single phase base MVA or base volt amperes, but for smaller quantities. In three phase system this is three phase base MVA or base volt amperes. That is the only difference which you have to remember. Otherwise, all three formulas are exactly same. All three formulas are exactly same. Let us try to solve this question. He's asking the per unit value of a 4 ohm resistor at 100 MVA base and 10 kV base voltage is. So he wants you to calculate the per unit impedance of the 4 ohm resistor. So what is the formula? Z per unit is equals to Z actual divided by Z base. So that is Z actual into S base divided by VB square. S base divided by VB square. So actual value of impedance is 4 ohm. What is the MVA base? It is 100 MVA. Base voltage is 10 square. So this value will become how much? 4 per unit. Here MVA and kV square will automatically cancel. kV square MVA automatically they will cancel. M means 10 power 6, K means 10 cube. So K square is equals to capital M, that will automatically cancel. Here the per unit value of 4 ohm resistor on these base values is 4 per. Suppose if he asks you to compute on a base of 10 MVA and 10 kV. Some other question, the same 4 ohm resistor, now the base value is this one. Then what will be the per unit value? Z per unit again is given by Z actual into S base divided by VB square. So 4 into S base is 10, V base is 10 square. So in this case, this value will become 0.4. The impedance value of a generator is 0.2 per unit on a base of 11 kV, 50 MVA. The impedance value of the same, this one on 22 kV and 150 MVA is. Try to solve this question and tell the answer. So he gave 0.2 per unit is the 0.2 per unit is the per unit impedance of a generator on a base of 11 kV and 50 MVA. So now we need to calculate the per unit value on a base of on 22 kV base and 150 MVA. So which formula we have to use? Z per unit 2 is equals to Z per unit 1 into SB2 divided by SB1 into VB1 divided by VB2 whole square, where 2 means new, 1 means old. So if you substitute in this formula, you are going to get Z per unit 2 is equals to, the old per unit value is 0.2, the new base MVA is 150, old base MVA is 50 because it was previously calculated on 50, now we are calculating on 150, so 150 by 50 into the old base value is 11 kV, now the new base voltage is 22 whole square. So this value you are going to get 0.2 into 3 divided by 4. So how much will be this value? 0.15 per unit. 0.15 per unit. So option A is the right option. Option A is the right option. Okay. The next question is, the per unit impedance of a synchronous machine is this much. If the base voltage is increased 1.1 times, then the per unit value is. So he did not mention anything about the base impedance. That means we have to choose the base impedance as same. So again, if we adopt the same formula, so Z per unit new will become, directly I am substituting the formula. The old per unit value is 0.242 here into, here the new base MVA and old MVA base values are same. I am writing SB and SP because there is no change in the base MVA values. But what he is telling, the old, if the old base value is 1 VB, now it is increased, new base value is 1.1 VB whole square. Then this value will become 0.242 into S base cancel into 1 into 1 divided by 1.1 whole square. So this will become 0.242 divided by 1.21, 0.2 per unit. So option D is the right option. Okay. So I hope you have understood. Try to. Anyone? Very simple question.
0.5x.
0.5x is the right answer. Okay. So Z per unit new again is equals to Z per unit old into S base new divided by S base old into V base old divided by V base new whole square. Here what he is telling, the per unit value is x per unit. Now we have doubled the base MVA, so that is it will become 2, it will become 1. Okay. Similarly, the voltage also doubled. The old, let us call 1 and new one will be this one. This is VB whole square. It is SB and SB. So if you do this calculation, you are going to get x into 2 divided by 1 by 4. So x by 2 is the new per unit value if you double the both. If you double both volt ampere base and the voltage base. Okay. So you simply remember the three formulae, then your per unit system questions are very easy. When you have to use, when you know actual impedance, you have to use one formula. When you already know the per unit impedance and you have to calculate new per unit value, you have to use this formula. Okay.